So this video we're going to be looking at oxidation states. So oxidation states are used in order for us to see what's been oxidised and what's been reduced in a redox reaction. So in an ionic compound, our oxidation state, also sometimes called oxidation number, is going to show us how many electrons have been lost or gained by the ion compared to the element in its uncombined state. But for covalent molecules, we don't have charged ions. However, we do still have a distribution between our elements in terms of where our electrons are lying, which we've looked at before when we looked at electronegativity. So here, our oxidation state tells us about the distribution of the electrons shared between the elements. And here we define that our more electronegative element is given the negative oxidation state. This brings about various rules. So to start with, every element in an uncombined state is 0. So this comes in from our ionic compound definition, where we said that it's comparative to the element in its uncombined state. Therefore, we must define our element in an uncombined state as 0. But also when we have diatomic molecules, then are such as Cl2, that will also be 0, as you have 0 difference in electronegativity, so you're going to have an even distribution of your electron density, and therefore you're not going to have one of the atoms that is pulling the electrons more towards itself than the others. As the same element, there's no difference in electronegativity. The other thing is just reminding us that if we have lost electrons, we become positive, whereas if we gain electrons, we become negative. So the more positive the number, the more it's been oxidised, whereas the more negative, the more it has been reduced. So unless they're 0, they must always have a plus or minus sign in order to tell us whether it's been oxidised or reduced. So some elements always have the same oxidation state, but others can have different oxidation states depending on what they're combined with. So the first ones to look at is our group 1, 2 and 3. because these are in ionic compounds, they always form +1, +2, +3 ions respectively. And then fluorine, being our most electronegative element, is always -1. So there's nothing that's going to stop fluorine from being -1, as it is the most electronegative element. Our second most electronegative element is oxygen. So oxygen we're familiar with being -2. However, in compounds where it's just oxygen and fluorine, such as OF2, it has a +2 oxidation state. And then in peroxides, it has a -1 oxidation state, but it's still more electronegative than the other species, so it's still the negative. But here it's positive because fluorine is more electronegative than oxygen. And then our hydrogen is normally +1, except when with hydrides, e.g. NaH, and then it is -1, and that's because our sodium is always +1, so therefore our hydride must be -1. Chlorine is less electronegative than fluorine and oxygen, so they're the two elements where when it's combined with, its oxidation state is going to change. So it's -1 unless with oxygen or fluorine. Another thing to remember is that overall compounds are neutral, and so it must all add up to 0. If, however, we had an ion, so complex ions, where you've got more than one element bonded together to make up that ion, then the oxidation state must add to form the charge of the complex ion. And then we have also established that our most electronegative element always has the negative oxidation state. So we'll go through a few examples. So going to start us off looking at a complex ion, so NH4+. Now we know that hydrogen is always +1 unless it's a hydride. This is not a hydride. Plus our nitrogen is more electronegative than our hydrogen, so we're expecting our nitrogen to be a negative sign. So we've got 4 hydrogens, so that's going to give us a +4, but ultimately we have to have a +1 charge. So to get from +4 to +1, we have to go down 3. So -3 plus 4 equals +1, which is the same as the charge of the ion. So therefore our nitrogen has a -3 oxidation state. Looking at a negative complex ion, so SO4 2-. So now we know that all our oxidation states must add up to -2. So oxygen is the most electronegative. It's not with fluorine and it's not a peroxide, so it's going to have a -2 oxidation state. We've got 4 oxygens though, so 4 lots of -2 is -8, and in order to make this -2, our sulfur is going to have to be a +6 oxidation state, because 6 minus 8 equals -2, which is the same as the charge of that complex ion. So we've started to see that actually we can have some various oxidation states. So we know that group 1 is always +1 and group 2 is always +2. And group 3 is +3. But 4, 5, 6 and 7, not going to worry about 8, they can have different oxidation states. So we just looked at sulfur, which had a +6 oxidation state in SO4 2-, and that's because it's group 6, so the maximum oxidation state it can have is +6, as that requires all outer electrons to be removed. And we can see that again with our group 5. So nitrogen had a -3 charge in NH4, and this is group 5, and this is the minimum as it's the most number of electrons that could be added to the outer shell. And thinking about this, we can then consider what our maximum of group 5 would be and what our minimum of group 6 would be, and also start to think about our group 4. So group 4, group 5, group 6 and group 7. So group 4, they have 4 electrons in their outer shell. So the most electrons that they can lose, and so then our maximum oxidation state, is going to be 4. So this would require all electrons to be removed, whereas for our minimum we need our most electrons added. Now group 4, they have the capacity to add 4 electrons, and so the minimum oxidation state will be -4. Group 5, we've looked at its minimum being -3, as it has 3 spaces in the outer shell for electrons to be added. But if we were to remove all 5 electrons from the outer shell, then we get our maximum oxidation state of +5. Group 6, we've looked at the maximum being +6, and our minimum therefore is -2 if we were able to fill that outer shell by adding 2 electrons. And similarly, our group 7, our minimum -1 if we were to add 1 electron in order to make it a full shell, and our maximum therefore is +7 if we were to remove all 7 electrons from our outer shell. Our transition metals also have variable oxidation states. Typically no higher than +7, but we can always work them out based on what else they are combined with, or sometimes they will use Roman numerals in order to distinguish between compounds with different oxidation states. So an example is our copper. So copper 1 oxide is going to be Cu2O, as we need 2 lots of +1 to counteract our -2. But we also have copper 2 oxide, so CuO. So that Roman numerals there are telling us the positive oxidation number of our metal. It's not just transition metals though that use Roman numerals. So the oxyanions of chlorine also sometimes use Roman numerals. So we often look at the chlorate ion, and that's given V, which is Roman numeral for 5, and that tells us that our chlorine is going to be in the +5 oxidation state. Now our chemical formula for this is ClO3-, and we could actually work out that +5 because we know that oxygen is going to be -2 because it's not a peroxide and it's not with fluorine. So we know it all needs to add up to our charge of our complex ion, which is -1. 2 lots of 3 is 6, so overall the oxygen is contributing -6, and in order to make sure that it adds up to -1, it's going to be +5. We also sometimes look at chloric acid, and that 1 there tells us it's going to be a +1 oxidation state of the chlorine, and here is our chemical formula. So we know oxygen is going to be -2, our hydrogen is going to be +1 as it's not a hydride, and it all needs to add up to 0 as overall that compound is going to be neutral. So 1 -2, at the moment we're at -1, and so that chlorine must be +1 in order to make sure it all adds up to 0. Some other ones that we don't normally look at A level, but I'm just going to include, is our chlorite ion, which has symbol ClO2-, and our hypochlorite ion is our one in chloric acid, and then also our perchlorate ion. So ClO-, and we've just looked at that's going to be +1, and our perchlorate is ClO4-. So this must add up to -1. Our oxygen is -2, 2 lots of 2 is 4, so something -4 gives us -1, so it must be +3, and so our oxidation state is +3. Similarly for this one, again adding up to -1, our oxygen must be -2 as it's not in a peroxide or bonded to fluorine, so 2 lots of 4 is 8, so something -8 gives us -1, so it must be +7 oxidation state. However, more commonly we're very familiar with chlorine having a -1 oxidation state, such as in sodium chloride, where the Cl iron has a -1 charge, but it's because here it's bonded with oxygen that actually now it has to be positive because it's less electronegative than our oxygen. But here hopefully you can see the full range of those oxidation states of chlorine. So all the way from -1 being our minimum and through to our maximum of +7. Also just want to take a quick look at permanganate. So an ion of manganese, transition metals with various oxidation states. So permanganate is our MnO4-, has to add up to -1. Oxygen must be -2 as it's not bonded to fluorine and it's not a peroxide. So 2 lots of 4 is 8, so -8, something -8 to give us -1 must be +7. And so here we would often see our permanganate with a V, II, to denote that +7 charge of our iron. Other transition metal ions that we commonly look at is our dichromate, which we use in organic chemistry from potassium dichromate in our oxidation of our alcohols, and there we have to look at our half equations for that. So our dichromate ion is Cr2O7 2-, and so to work out our oxidation state here has to add up to -2 to meet the charge of the complex ion. Our oxygen is going to be -2 because it's not bonded to fluorine and it's not in a peroxide. So 2 lots of 7 is 14. So something -14 equals -2. So it must be +12. But this is for 2 chromium atoms. And so each one must have half of that on average. And so we're going to give it a +6 oxidation state. And so we might see it with a VI in order to denote that +6 oxidation state of the chromium in the dichromate. Okay, just to recap what we have covered. So we've looked at what the oxidation state tells us for an ionic compound in terms of redox, and what the oxidation state tells us for a covalent molecule in terms of electronegativity. Which element is given the negative oxidation state, what are the rules for assigning oxidation states, what must the oxidation states add up to for a compound, what must the oxidation states add up to for for complex ions. How to calculate oxidation states where they vary. What is the range of oxidation states for groups 4 to 7? What are Roman numerals used for? And then just want to point out with our transition metals, these are still always positive because they are metals. And then finally we looked at what are the different oxidation states of chlorine, and how to work out the variable oxidation state of transition metals in complex ions. So even if we haven't come across an ion before, we can work it out using either our Roman numerals or from the chemical formula that they would have given us. But permanganate and dichromate are definitely two that you should learn.